Yes, yes, I'm there.
Good afternoon.
Good afternoon.
Professor Gajare, can you please, yeah, you have already stopped presenting. Fine. Yeah, Dr. Nelson, may I request you to, switch on your video so that people can see whom they are going to listen.
Sir,
Yes,
your
yes.
mic is muted.
Yeah, nice to see you after a long time.
Yeah, nice to see you as well.
Yeah, thank you. Good afternoon, dear participants. We have Dr. Nelson Muthu, who is Associate Professor in the Department of Mechanical Engineering at Indian Institute of Technology, Guwahati. Dr. Nelson, I must introduce you to the participant in the beginning and then I'll hand over the session to you.
Okay.
Participants, Dr. Nelson Muthu is a product of three well-known universities. IIT Guwahati, where he did his BTech in the year 2008. IIT Bombay and Monash University, where he completed his PhD in 2015 on application of element-free Galerkin method for linear elastic fracture mechanics problems. After his PhD, he has worked at Biomedical Engineering and Technology Incubation Center at IIT Bombay on medical device innovation from December 15 to July 17. He was a visiting faculty at Sardar Patel Engineering College, SPCE, Mumbai for some time. Parallelly, he also worked on structural health monitoring project, which involved detection of cracks in beam-like structures. He has corporate experience as an analyst at Global Analytics Chennai from July 8 to July 10 after his graduation, where he learned predictive analytics using statistical modeling techniques. Dr. Nelson Muthu's research area include composite materials, fracture mechanics, damage mechanics, mesh-free methods, and biomedical device innovation. He has more than 20 research articles published in international journals and conferences of repute. He has guided 12 master students already and 19 bachelor students on various projects. Presently, you will not believe, presently he is guiding 10 PhD students simultaneously at IIT Guwahati. And I have come to know from some of the aides from his department that, he is one of the best teachers in the department. He gives regular talks on computational fracture mechanics, fatigue, and biomedical device innovation in academic institutes and industries. With this brief introduction, may I now request Dr. Nelson Muthu to take over his session titled Plastic Zone Correction and Duckdale's Model. Thank you. Over to you, Dr. Nelson.
Yeah. Thank you, Professor Sachin Naik. Was in fact a detailed introduction. So what I'll do is I'll share the screen, and if audience participants have any questions at any point of time, they just can interrupt me, or they can also ask questions at the end. I will open the platform for questions at the end as well. Thank you. So can I keep the video on, or how should I go about it?
It depends on you. If you have enough connectivity, that's not a problem. It's up to you.
Okay. Yeah. So is it visible?
Yes.
I am in the second slide.
Yeah, you are on the second slide now.
Yeah. Okay. Thank you. So before going ahead with this plastic zone correction factor, I would like to give a quick introduction on why such a topic is required. Because most of the fracture mechanics that is generally taught in the university levels is mainly to do with linear elastic approach. Now, if you look at the linear elastic approach, although it involves a lot of math, yet the final equations that we receive are nice looking. Here, once you get the derivations and the concepts clear, you will be in a position to appreciate the concepts related to linear elastic fracture mechanics. But in reality, you will not see that these concepts are going to be perfectly, applicable to any material, because even in so-called brittle materials, there is going to be some element of yielding, just ahead of the crack tip. If that is the case, in day-to-day, if you see the materials that are being used in infrastructure or in automobile or aerospace applications, typically they are, metals or composites. There is going to be some yielding, or sometimes we also refer to that process as small scale yielding or modest yielding. These are the terminologies that are used. So in such cases, it is difficult to apply the linear elastic fracture mechanics concepts, because they exhibit some amount of yielding. So in such scenarios, we need to reorient some of the concepts that we learned as part of linear elastic fracture mechanics framework. From henceforth, I'm going to use LEFM in place of linear elastic fracture mechanics, because that becomes easy. So in LEFM, if you see carefully, the stress field ahead of the crack tip, it is a singular stress field. So you can see here, let us say in this case, there is a object with an edge crack. So this is shown to you here, it's an edge crack. So this edge crack, as it opens under the loading, here it is a tensile loading. So it is going to open, and in the LEFM framework, your stress ahead of the crack tip, for example, sigma yy, that is going to be singular in nature. By singular, what I mean is this, that the stress just ahead of the crack tip is going to be infinite. Now, in reality, this is not at all possible, because in any material, even if you take, for example, brittle material, the stresses are going to be finite. No material is going to withstand infinite stress. Therefore, there is a problem. And this problem is further amplified in the presence of inelasticity, or in the presence of plasticity in metals, or crazing in polymers. So, therefore, we will, change some of the concepts that we have learned as part of LEFM. We are not going to change everything, but small concepts. Essentially, you need to understand that these are all models. These are mathematical models used to fit solving some materials, crack propagation in some materials which exhibit small scale yielding or modest yielding. Okay, so that is the objective. Now, as the inelastic zone at the fracture tip increases, the elastic stress analysis becomes progressively erroneous. So that is the issue. So how do we avoid this? Or we cannot, again from the scratch invent the fracture mechanics analysis for elastic plastic materials, because that is going to take a lot of time, and it is not also straightforward. The analysis, even the derivations are going to be humongous. I mean, it is going to be very big. Therefore, how do we, as an engineer, how do we actually bring forth some modifications in the existing theory so that it can also be used for such materials? So that is going to be the objective for the next 2 hours. So when modest crack tip yielding occurs, as I said, it is not a very high plastic material, but it is you can understand this way. It's a small scale yielding, or the plastic zone, the size of the plastic zone, that is restricted to a small portion in the region around the crack tip. Okay, so that is what is this term modest means here. Okay, it is a vague term, but what I meant is this. So if you have a crack like this, and if you have very big plastic zone, for example, something like this. These images are not to scale, but just to give you understanding, I'm drawing this. But if this is the size of the plastic zone versus, there are also materials where the size of the plastic zone is so small. So in such cases, these theories that I'm going to discuss for the next 2 hours, they are going to be useful. So specifically, I'm going to focus on the Arvin's methodology and the strip yield model. They can both be used to estimate the size of the crack tip yielding zone. So first, I'm going to focus on Arvin's methodology, how he understood the phenomena and how he took care of it. I'm going to present it, and then followed by the strip yield model. The strip yield model was independently proposed by 2 researchers, Duckdale and Barnablet. So I'm going to also show that derivations as well. It is also interesting to show that Arvin's methodology and the strip yield model, almost give similar results. Now, what is this Arvin's model? Okay, basically, there are 2 classifications under Arvin's model. One is that it is a first order estimate, and another is a second order estimate. The first order estimate is a very simplistic model, and then we are also going to see the second order estimate. So the first order estimate says this. As a first order estimate, I'm also calling this as a first step. Okay, so what it says is that we can assume that the boundary between elastic and plastic behavior occurs when the stresses satisfy yield criteria. Okay, I just repeat. The boundary between the elastic and plastic behavior occurs when the stresses satisfy a yield criteria. This is something that we can very well appreciate. So here you see, in this case, we have the stresses, singular stress field using linear elastic fracture mechanics framework. But if you take elastic perfectly plastic material, so in all the discussions for the next 2 hours, we are going to restrict ourselves to elastically perfectly plastic material. So what is this elastic perfectly plastic? So if you see in any non-hardening material or elastic perfectly plastic material, the stress versus strain behavior is going to something look like this. Okay, so this is proportional. Your stress is proportional to strain in this region up until this region. After this, once the stress reach the yield stress, so this is going to be the yield stress sigma ys, and it is going to remain as it is. So that is what is called perfectly plastic material. So Arvin's methodology and the strip yield model was derived keeping in mind that the materials exhibit elastic perfectly plastic behavior, or in other words, the material exhibits non-hardening behavior. Okay, so in that case, as a first step, if you were to find the length ahead of the crack tip, up to what length? So you see here, this is the crack, this is the crack here. Up to what length it is going to exhibit plasticity, that can be very easily found out by using this equation. So what is this equation? You must be familiar with this equation, right? Sigma yy is nothing but k1 by square root of 2 pi r. So as you must have realized, when r is equal to 0, sigma yy shoots to infinity. That is why this stress field is called singular stress field, or sometimes it is also called asymptotic stress field, because it is varying asymptotic in nature. So now, if you see, whenever the stress reaches the yield stress, whenever the sigma yy, when it becomes sigma ys, then you would say that point is going to be the boundary point. Okay, or in other words, that is the boundary between the elastic and plastic behavior. You see here, so this lambda is going to be the length of the region which is under this plasticity. So you can see here, because it is elastic perfectly plastic from the crack tip up until this point, up until this point, or RP. So this RP stands for the distance from the crack tip where the plasticity ends. Okay, where the material does not exhibit, henceforth from RP, the material does not exhibit plasticity. So that is what the term RP means. So we will use this RP and lambda again and again. But you also can see here there is a term called A here. A denotes the length of the crack. Okay. So you can see here just at the point along the x-axis, that is at point RP, your stresses sigma yy is going to be equal to sigma ys. Okay. So now this point is the boundary point. So now Arvin, he in the first as a first step, he said that lambda is going to be the length of this plastic zone. This is along the crack line. Please note that it is not somewhere along theta is equal to not 0. So for example, if this is the crack, so only along this crack line, if the crack were to extend, so in the self-similar direction, so this lambda was estimated, not in any particular arbitrary theta. Okay, if you take any arbitrary theta and if you want to estimate this length lambda, it is not possible, only along the direction of extension of the crack. That is in the case of mode 1, the crack is always going to propagate straight under the action of tensile loading. So in that case, just along the crack extension direction or along the crack line, the lambda was estimated as a first step. So now, what is this sigma ys? Why did I put 2 sigma ys and there is also 3 sigma ys? Now this first step was calculated. This lambda was calculated assuming that the material exhibits plane stress condition. Okay, so because you see in plane stress, your third principal stress is going to be 0, right? Because plane stress you have sigma 1 and sigma 2 as non-zero. The third principal stress is going to be 0. So using the Tresca's condition, you can realize, the Tresca condition says that the material is going to exhibit yielding when sigma 1 minus sigma 3 by 2 is nothing but sigma ys by 2. Okay, so that is the Tresca condition, or sigma 2 minus sigma 3 by 2 is equal to sigma ys by 2, whichever is maximum. Okay, so this was a condition that we can use. One can also use von Mises condition as well, but in the plane stress, sigma 3 is equal to 0. And if you have observed carefully, in the case of the stress field ahead of the crack tip in mode 1, your sigma 1 will be equal to sigma 2 along the crack line. Okay, when theta is equal to 0, both will be equal. So in such a scenario, naturally your sigma 1, let us say in this case, because sigma 1, sigma 2 are equal, in the plane stress case, your sigma 1 has to reach sigma ys. Then only the material is going to yield. So that is why I have put here sigma ys. In plane strain condition, the things are going to be slightly different. You will have to have a higher value of sigma 1 for the material to yield. So you can see here. So what I have covered in this slide is this. As a first step, Arvin had to find out the distance along the crack line where the plasticity would end, or the material would only exhibit elasticity. So that point can be straight away found out by setting theta is equal to 0 in the derivation of the stress field. And then whenever sigma yy will be equal to sigma ys, corresponding to that, you can find out what is the value of r. In this case, r will be nothing but rp. In that instance, your sigma y will be nothing but sigma ys. So now this sets the stage for the advanced theories. So as a first order estimate, as I said to you before, once you neglect the strain hardening and for plane stress, the yielding will occur when sigma yy will be equal to sigma ys. Again, this is based on the Tresca's criterion, and sigma ys is nothing but the uniaxial yield strength of the material. So you can use this, straight away. You can use this relation k1 by square root of 2 pi lambda. This will be equal to sigma ys. Okay, so from there you can estimate what is the value of lambda. So that means what? Once you know the SIF, then you will be in a position to find lambda. Okay, and because SIF is something that is very characteristic of a material, in LEFM analysis, SIF, also yield stress, then you can be in a position to find out lambda. Okay, so this lambda is nothing but the region, along which you can see that the plasticity or the material exhibits plasticity in that region. Right. As you know, in solid mechanics or strength of materials, it is important that we satisfy the equilibrium equations when we try to solve the problem. Specifically, the equilibrium condition was not able to be satisfied because of this. If you see this carefully, in the case of crack in the elastic material, if you solve using LEFM approach, then this would be the stress field. What you see here, this is elastic stress field. But because of the first order estimate, in the presence of elastic perfectly plastic material, the highest stress that we could achieve is the yield stress of the material. And if you see this carefully, in the portion lambda in this region, there is some contribution of force, due to sigma yy. So that the hatched portion that you see here, this is going to, give rise to some force, which is not taken into account in the case of first order estimate, because you see the elastic stress field starts from here, it almost starts from infinity and then it drops down, but the sigma ys, the elastic perfectly plastic stress, that starts from here. So there is some loss of force contribution due to the elastic perfectly plastic analysis in the first order estimate, which should be accounted for. Otherwise, where would we account for this force contribution due to the hatched portion? So that is going to be the rectification or redressing of the first order estimate, and it gives rise to the second order estimate. In the second order estimate, what we do is this, that we equate the total force. Actually, if you want to calculate the total force, you also need to take into account of the thickness of the specimen. But if you take the thickness of the specimen on the left hand side and the right hand side, assuming the thickness is going to be constant, it gets anyway cancelled out. So B is going to be the thickness of the specimen, which we generally use. That is a symbol that is used in fracture mechanics to denote the thickness of the specimen. But so if B is out of the equation, then you have the net force contribution due to the singular stress field from 0 to RP. Now RP is what? RP is the new definition for the plastic zone size, right? So the new definition of the earlier we had the definition of the plastic zone size as lambda, and this lambda is also called the plastic zone correction factor. Why it is called plastic zone correction factor, I'll come into it later. But let us say we are going to determine a new value of lambda. In this case, let us use this symbol RP. So from 0 to RP, 0 in the sense the reference is the crack tip. So from 0 to RP, so you see here 0 to RP on the bottom right hand of the slide. So the total force contribution due to elastic perfectly plastic analysis should be equal to the total force contribution from the elastic stress field. Okay, so that will sort out the issue that is there in the first order estimate, because there was force imbalance. But here we are trying to actually make sure that the equilibrium conditions are satisfied by making sure that the net force due to the elastic stress field in the region 0 to RP will also be equal to the force contribution due to the sigma ys in the span 0 to RP. So that is the underlying principle. So naturally, if you see, from 0 to RP, because this is a plastic zone and this is elastic perfectly plastic material, the stress is going to be constant. That is why I put sigma ys. Okay, and sigma ys into RP, this is the proxy for the force contribution due to the elastic perfectly plastic material in the region 0 to RP. Now, so this term, either k1 by square root of 2 pi r. So what is this term? This is nothing but sigma yy. Sigma yy along 0 degrees. 0 degrees in the sense if you have a crack, and this is going to be your x and y axis, and this is going to be your r, and this is theta. So this is how it is, but all the analysis, Arvin's methodology or Duckdale model / repeat model, they are all concerned about the events that are happening along the crack line. That means along theta equal to 0 degrees. Okay, we are not worried about what is happening at theta is equal to some other arbitrary angle which is non-zero. Okay, so you must understand that these are all models, right? So because you see, it is very difficult to actually solve a fully elastic plastic material, and it is also tedious. It is almost impossible to get a full field solution. The stress field and displacement field solution for elastic plastic material. So as an engineer, we cannot spend a lot of time investigating or trying to get the full field solution of elastic plastic material. But on the other hand, we have full field solution for the linear elastic material. So we must make use of that. And we also must, get some models which can be equivalent to, elastic plastic material. So that has been the objective. So making use of these LEFM principles that we have learned, we are going to use and extend these principles to elastic plastic material. How do we do that? We bring in some models or we make some mathematical approximations. That is what is happening in Arvin's methodology and Duckdale model. So in this case, along theta is equal to 0 degrees, this direction, if you see this carefully, now this direction along this strip, along this ligament, let me use this word ligament. So along this ligament, we want to see how much is the length of the plastic zone. So that length, if you do this, force balance due to elastic field and elastic perfectly plastic field from the span 0 to RP, you are going to get the value of RP as 2 lambda. Okay, that means what? Your length of the plastic zone, using the second order estimate is twice the length of the plastic zone using the first order estimate. Okay, so that becomes very convenient. Now, what are we able to see? We are able to see our model, this Arvin's methodology. This model has given us a picture that the size of the plastic zone, if it is 1 by pi, what you see here on the bottom end of the slide, 1 by pi K1 by sigma ys whole square, then you can use the linear elastic fracture mechanics principles to solve the elastic perfectly plastic material, although it has a plasticity in it. It has some plasticity in it. So that is the final goal. We don't lose the plasticity, at the same time we don't lose LEFM principles. So we bring it together, and that has been brought in this framework of Arvin's methodology and Duckdale's model. Now you must have realized, that when we calculate this lambda or when we calculate this RP, essentially we got a model, right? And that model is able to take into account of all the plasticity along that strip, along that ligament. Okay, but what do we do next? How do we proceed ahead with the analysis? So we proceed ahead with, finding a new crack length. See, earlier in the elastic analysis, the crack length was A. And please note that the SIF is only, SIF is only defined in LEFM framework. If you go for plasticity, inelastic behavior of the material, or if you want to analyze non-linear elastic materials like hyperelastic materials, there SIF does not make sense at all. There we have to make use of the concept of energy release rate. Okay, so if you want to make use of this SIF, that means you can only make use of that in that LEFM framework. But what you have now is a methodology, Arvin's methodology specifically, where we brought that sort of ligament into picture and we compressed all the plasticity in that ligament. Okay, so now so once we develop that mathematical model, the question remains, can we in any way bring this LEFM principles to apply to this model? Now, how can we do that? This can be done by defining a new crack length. How do we define the new crack length? We define, so Arvin proposed that actually in the presence of plasticity, if this is the crack length A, naturally, because of plasticity, the region around the crack tip is going to become little soft. That is because the material is flowing due to high stresses. So now the crack faces slightly will become like this. It'll the displacements, it is going to blunt, it is going to actually expand little more than what was before in the case of elastic material. Now, if you have to equalize, this is the behavior in the case of, elastic perfectly plastic material. But if you want to make it equal to that of an elastic material, what you would do is you would extend the crack. Okay. But if you observe carefully, the physical crack tip is only here. But we are just mathematically extending, we are just mathematically extending so that this, when you actually, perform linear elastic analysis on this crack, on the extended crack, it is equivalent to the crack in elastically perfectly plastic material. I repeat it again. See, in the case of elastic perfectly plastic material, when there is a crack, the edge displacements of the crack is more than the edge displacement of the crack had it been in elastic material. Now, how do you equalize this? The easy way to equalize this is extend, fictitially, you are not actually sort of, extending the physical crack tip, but you are just, extending it fictitiously. I mean, in the sense that there are going to be two crack tips. One is that, you are going to have a physical crack tip here, and then there is a mathematical crack tip here. Okay, so the mathematical crack tip is sort of, it's a virtual. You're not able to see it. But then, if you take that as the tip, this mathematical tip as the crack tip, and if you perform all the analysis using LEFM principles, you are going to get the same results to that of crack in elastic perfectly plastic material. See, that solves the problem. That is what we wanted to do. We cannot solve, even analysis of, so strength of materials analysis of elastic perfect plastic materials or elastoplastic materials are going to be tedious in nature. How much more it will be tedious it will be when you want to analyze a crack in the presence of yielding, when the material is yielding. So how do we extend this crack? By what length we have to extend this? Fictitiously, you can extend by any amounts, but Arvin suggested that the elastic crack of length A, if it is there, if it is there in the elastic perfectly plastic material, then when you extend by lambda, then the effect, the result, the net results are going to be same. Okay, so this effective crack length is given by A plus lambda. So you know what is lambda? Lambda is nothing but the first order estimate, which is given by 1 by 2 pi k1 square by sigma ys whole square. So now you see here, that is the beauty of this. By fictitiously extending this crack, why did I extend by lambda? I will also come into it later. Why not 2 lambda? Why not RP? Okay, there is a reason for it. So now by extending it, although the crack is an elastic perfectly plastic material, or let us say the material is undergoing small scale yielding or modest yielding, still you are able to use the effective SIF concept. The effective SIF corresponds to the effective crack length. How does it correspond? K effective is given as function of geometric parameter as well as loading, far field loading, as well as effective crack length. Okay, so that is the advantage. You see, so I'll just summarize. The objective is to make use of the LEFM principles in the case of elastic perfectly plastic material. But we were not able to use it because SIF is not defined for inelastic behaving materials. Therefore, we had to make some adjustment. The adjustment was based on some mathematical model. The first mathematical model that we saw was first order estimate, and it was not able to satisfy the equilibrium. Therefore, we went to second order estimate, and we understood that if we have a ligament of length RP, then we can satisfy equilibrium as well as we can bring all the effects of plasticity in that ligament. Okay, having brought that effect into that ligament, we still were not able to make use of the LEF principles because they are very neat and concise and precise. Although the math is tedious, but still once you get understanding of it, it is easy to apply. The entire thing LEFM revolves around this SIF. Therefore, our critical parameter of interest for us in the case of a crack, whether it let it be in LEFM or even in elastic perfectly plastic material would be SIF. If you could actually bring that sort of concept into picture. Therefore, we extended the crack by lambda. Why we extended the crack by lambda? See here on the bottom end of the slide, there is a crack of length A, elastic, perfectly plastic material. So here you have the physical tip, and we have extended the crack by lambda, mathematical tip. How it is possible? Because you see, when you extend the crack by lambda, if you were to solve this problem using LEFM, naturally you would have got this as a solution. So singular stress, it is asymptotic stress field. So that has been the solution. But because it is elastic, perfectly plastic material, in this region, you are going to have sigma ys. So all the stress is going to be sigma ys. So what will happen to the contribution due to this stress field in this region A1, the purple region? So when you extend by lambda, it has been shown that A1 is approximately equal to A2. Equivalently, it is equivalent. So that has been the basis. So when you extend the mathematically fictitiously by lambda, whatever has been the loss due to the elastic stress field, the force contribution, that has been already taken into account, in A2. So that became the basis. Now it becomes very easy. So one can actually still, apply these LEFM principles in the case of elastic, perfectly plastic material by making use of such models. How do we calculate this K effective? It is iterative process. That is why some people they have some sort of inhibition to use this Arvin's methodology to calculate effective stress intensity factor. So how do we do it? Is first we assume that the crack is only inside the elastic material. There is no plasticity. So in the absence of plasticity, we calculate K. So once we calculate K, so how do we calculate K? That is very straightforward. If you have a crack in infinite material, center crack in infinite material, K is going to be sigma root pi. Okay, and if you have finite geometry, you are going to have a geometric correction factor also. But in real life scenarios, all the materials that you are going to encounter is finite in size, and therefore you are going to have some geometric correction factor y of A. Okay, but at this point of time, let us leave this. So once you have this K is equal to sigma root pi A, then you can determine what is going to be your lambda, first order estimate. That is going to be 1 by 2 pi, Ky by sigma ys whole square. Okay, so once you have this lambda, what you do, you will calculate A effective, A plus lambda, right? Because A corresponds to the physical crack length and lambda is the correction factor. We are extending the crack mathematically. So that is the third step. And the fourth step is what? Once you calculate AEF, you are again going to calculate the AEF. The third step, once you calculate AEF, you are going to calculate KEF again. KEF can be calculated, K effective can be calculated by using this relation, AEF. Okay. So this process is iterated. So again, you see this is sort of similar. So once you have KEF, then you are going to calculate lambda, and then you are going to calculate new AEF, and then you are going to calculate again KEF. So this process becomes iterative. You are going to do this until you find a convergence in KEF. In other words, the change in KEF is going to be small. Okay, so that is how you are going to estimate the KEF. For your understanding, I have put this different modes. This is something that some of you may be already familiar of. See, this is mode 1. Mode 1 is opening mode. And if you see carefully, you can also look at the contour plot of the stress. And this is the mode 2. It's a shear mode. And this is mode 3. This is tear mode. This is opening mode. Now, let us focus on the mode 1 problem. If you have already seen the derivations of the crack tip stress field, then you would have noticed that this sort of expressions for the stress in the region surrounding the crack tip. Specifically, you will see that there is going to be the SIF, mode 1 SIF, and there is R, and it is also a function of theta. So what is this SIF? Sometimes in my class when I talk about SIF, students understand that it is something similar to SCF, stress concentration factor. SCF does not have units, but SIF has units. We use megapascal Root meter. So the SIF is something that we can understand, and it is kind of a variable like that of a scaling factor. It is a parameter that sort of tells you the power of the crack. And once the crack is powerful, you will see the stresses, the stress field around the crack, that also is sort of influenced by that parameter. So that is how SIF is. So if you see this carefully, if you can actually make this SIF 0, then the whole problem, in the sense your stress field, your stresses reaching to infinity, the point just ahead of the crack tip, that is going to be eliminated. We do not want infinite stresses in any material. No material can actually withstand infinite stresses. But because of the theoretical framework in LEFM, we are getting that sort of behavior. So if we can make the SIF 0, then this singular problem, singularity problem, that will be eliminated. So in fact, that is going to be the basis for the Duckdale model. They are going to make the net SIF equal to 0. Okay. So now, if you see this, you are able to see the stress field sigma xx and sigma yy, and you also have tau xy as well. For mode 1. So for plane stress, obviously the stress in third direction is going to be 0. For plane strain, third stress in third direction is going to be nu times sigma xx plus sigma yy. So yeah, now the question is, what will be the shape of the plastic zone? So you can use various criterion. Tresca criterion has been routinely used to determine the shape of the plastic zone theoretically. In some cases, people also use von Mises criterion. In fact, if you see carefully von Mises criterion, there is a clear distinction between plane stress and plane strain, and therefore it becomes very easy to represent that as well. So here I will show both the Tresca criterion as well as von Mises criterion. Based on this criterion, how will the plastic zone shape looks like in the case of mode 1, mode 2, and mode 3. Okay, Tresca criterion, if you have principal stresses, sigma 1, sigma 2, and sigma 3, you will have to find the maximum of the difference of these stresses. Sigma 2 minus sigma 3 by 2, and then you have sigma 1 minus sigma 3 by 2. So you'll have to find the max, and that should be equal to the shear stress at the point of yielding when you conduct uniaxial tensile test. Okay, so that will be going to be sigma ys by 2. Okay, so in the case of plane stress, you have sigma 3, the principal stress, the third principal stress, that is going to be equal to 0. So naturally your sigma 1, so if you bring in this expression, so sigma 1 minus sigma 3, in this case it is 0, should be equal to sigma ys by 2. Therefore, your sigma 1 is nothing but sigma ys. So this has been the basis for us to find the plastic zone correction factor in the case of first order estimate. We also said that you are, if sigma 1 is equal to sigma ys, if you see carefully along theta equal to 0, because in that ligament is our focus, along theta equal to 0 degrees. So if you put theta equal to 0 degrees in sigma x and sigma yy, then both are going to be equal. Okay, so so you see here, when sigma 1 is equal to sigma 2 is equal to sigma ys, if that sort of condition with is imposed, then you can get the plastic zone correction factors for plane stress. But what about plane strain? Plane strain is a little bit different. Why it is different? Because you have Poisson's ratio into in the picture, and we have to definitely bring that sort of effect of Poisson's ratio into the analysis as well. So right now what we'll do is we'll assume Poisson's ratio to be equal to 1 by 3. 1 by 3 is equal to 0.33, and that is the value around which most of the day-to-day real-life materials in structural applications or aerospace or automobile applications will have its Poisson's ratio, around that value. So now the question is, if you take nu is equal to 1 by 3, and if you take then sigma 3, what will be sigma 3 going to be? Sigma 3 is going to be 1 by 3 times, sigma 1 plus sigma 2, right? But, in this case for mode 1, along theta equal to 0 degrees, your sigma 1 is equal to sigma 2, that we already seen from these expressions. We are able to see that. So it is going to be, let us say, 2 alpha by 3, where sigma 1 is equal to sigma 2 is equal to alpha. Okay, so now you see here there is a non-zero stress. The stress in the third direction, the principal direction, you see there is a non-zero stress. So if that is the case, if you have a non-zero stress in the third direction, naturally to attain the yielding, for the material to yield, you will have to have a very relatively higher value of sigma 1 or sigma 2 for the material to yield. So you see here, this is the situation in plane strain. So now you see again, from these expressions using Tresta condition. So you see this expressions. If you actually put the value of sigma 3, let us say in this, then it is going to be sigma 1, or in this case, it is going to be alpha, alpha minus 2 alpha by 3 divided by 2 is equal to sigma ys by 2. And if you solve this, your alpha is going to be 3 times sigma ys. So you see here, your alpha, that means alpha is what? Sigma 1, you can see here. So sigma 1 equal to sigma 2 is equal to alpha. That means you have to reach that 3 sigma ys for your material to yield, in plane strain. Whereas in the case of plane stress, your sigma 1 has to be equal to sigma ys. Okay. So that is why you see here, the plastic size of the plastic zone, it is reduced. You see here, only this region, this lambda, this lambda is the region where your sigma 1 or sigma yy, that reaches, 3 sigma ys. So what you can see here is that when k1 by square root 2 pi lambda, when it is equal to 3 sigma ys, you will get the value of lambda as 1 by 18 pi k1 by sigma ys whole square. Whereas in the case of plane stress, lambda was how much? 1 by 2 pi, ki by sigma ys whole square, or k1. Okay, that means your plastic zone size in the case of plane stress is much higher than, it is almost in this case 9 times higher than what you see in the plane strain case. So what is its implication? See, when you actually want to design some material, using strength of materials approach, how do you design it? We always have this notion, if the material is big, then it is able to withstand load. The factor of safety for that material is quite high. Therefore, we can comfortably, design the material so that we can avoid failure. If you have, very high dimensions of the material, that is the norm in strength of materials or solid mechanics. But in the case of fracture mechanics, there is a counterintuitive view. What is the counterintuitive view? For example, if you have a crack in a material and there is one material, it's a thick, one material is thick, another material is thin, and you have same size of, same size crack. Let us say the length of the crack is A. Now, if I were to ask you which material would you choose so that you can avoid failure due to crack propagation, will you choose a thick material or a thin material? The fracture mechanics concept says, that you have to choose a thin material. The reason is this: in the case of thin material, lot of energy goes into plastic deformation. Relatively less amount of energy is available for the formation of new surfaces of the crack. Formation of the new surface of the crack is nothing but crack propagation. Whenever crack propagates, two new, small new surfaces are formed. For any new surfaces to be formed, you require energy. When you also design helmet, for example, bike helmet, motorbike helmet, we use foam, like material in the helmet. And when there is an impact, this foam, this kind of material breaks into multiple pieces. Why is that it breaks into multiple pieces? Ideally, we would have thought that, we should actually, design a helmet which doesn't break upon impact. For people who use bikes, if there is any impact, naturally one would advise not to use the helmet, because the material inside it must have broken into multiple pieces. Why is that important? That is important because all the energy that has been transferred by the impact to the person, that goes into the formation of new surfaces. That has been the principle here also in the crack propagation. So when the crack propagates, two new surfaces, upper new surface, lower new surface, they are formed and then they require energy. And if the energy is spent in plastic deformation itself, where is the energy available? Less amount of energy is available for the propagation of crack in thin materials. Whereas in thick materials, because the size of the plastic zone is relatively smaller, more energy is available for the formation of crack faces. That is why the crack propagation rate is higher in thick materials and it is lower in thin materials. Anyway, we'll come back to it later at the end of the lecture. But what you have to realize is the size of the plastic zone, lambda, here is 9 times smaller than the size of the plastic zone in the plane stress, using first order estimate. Now, there was a problem. The problem was that, Arvin, when he was doing some more work, he found out that the stress at which the yielding stops, that is not 3 sigma ys. Oh, there is a typo here. It is 3 sigma subscript ys. But it is lesser due to following factors. Why it is lesser? Because the crack tip blunts due to the plasticity. And the tip acts as a free surface. What is its implication? So when you have a blunt crack, and when you have the sigma xx as 0 on the free surface, it's free surface, right? So therefore your sigma xx is 0. That means the effect of sigma xx is felt along the crack line to some distance. So what is the result of this? That means the principal stress in the second or third direction, that is relatively less. It is approaching that principal, the plane stress kind of situation. Okay, so because of this crack tip blunting due to the plasticity, sigma xx goes to 0, and therefore using the Tresca criterion, the stress that is required to initiate the yielding is much smaller than what we had used in the previous derivation. So it was found out that the failure stress was estimated to be around square root 2 root 2 sigma ys. How we got that? That we will not look into it. But now, for a moment, just take it for granted that this is the value at which the material yields. That experiences up to this value. Or in other words, let me rephrase it. So when your sigma yy, when it reaches this value, then we can say that, we can, at that point, we can find out the plastic zone correction factor. So it is approximately equal to square root 3 sigma ys. You mathematically do it, they're almost equal. So in place of square root 2 root 2, we are putting square root 3, and then this is the expression for sigma yy in the case of mode 1. And then when you use on the right hand side the expressions, because of the above mentioned reasons, you are going to get the value of lambda as 1 by 6 pi k1 by sigma ys whole square. But still, the size of the plastic zone is lesser in the case of plane strain compared to plane stress. Right? So now, if you want to use the second order estimate, like in the case of plane stress, if you also want to use the second order estimate to attain or to achieve equilibrium, you will get an expression like this: Rp is equal to 2 lambda. So in the case of plane strain, your Rp is going to be 1 by 3 pi k1 by sigma ys whole square. So that is the contrast between plane stress and plane strain. Now I want to also show you the shape of the plastic zones. Okay, so for the shape of plastic zones, we consider the principal stresses. Sigma 1, sigma 2, you can see here. It is not very difficult to actually obtain the principal stress. And on sigma 3 is going to be nu times 2 k1 by square root 2 pi r for plane strain. So what I'm going to do is, I'm going to actually show different shapes of the plastic zone using Tresca criterion as well as the von Mises criterion. In order to do that, in the case of Tresca criterion, I use this expression sigma 1 minus sigma 3 is equal to sigma ys. Okay, so sigma 3, in the case of plane strain will be non-zero, It is not necessary that one has to use sigma 1 minus sigma 3. Sometimes we have to use sigma 1 minus sigma 2. We have to see which is smaller, whether sigma 3 is smaller or sigma 2 is smaller. Accordingly, we have to use the equation for yielding or for finding the shape of the plastic zone. Anyway, so once you use this equation, sigma 1 minus sigma 3 is equal to sigma ys, you are going to get an expression like this for plane stress or for plane strain. Okay, so this ry of theta, what is this ry of theta? This is going to tell you at what distance you are going to have that boundary. So basically, I'm going to plot the boundary of elastic plastic region. Okay, so in that boundary, it is going to be the material is going to yield. Outside that boundary, the material is still under elastic stress field. Okay, so this ry of theta, instead of plotting ry of theta, I'm going to plot a normalized version of a plot. So ry of theta divided by k1 square by 2 sigma ys square into pi. So this is going to be my plot. Okay, so I'll just bring this this expression here. Okay, so I'm going to plot something as a function of theta. So again, making use of this Tressa criterion, so I will plot for sigma 1 minus sigma 3 is equal to sigma ys. I will also plot for sigma 1 minus sigma 2 is equal to sigma ys. You can see that. So you see here, this is going to be the shape of the plastic zone. For plane stress, obviously, as we have already seen, your size of the plastic zone is comparatively higher than what you have seen in plane strain. So in plane strain, your sigma 1 minus sigma 3, this, if you use this criterion, you can see the size of the plastic zone, which is so small. Whereas if you use sigma 1 minus sigma 2 is equal to sigma ys, it is slightly bigger. So essentially, what we have to see here is the size of the plastic zone in plane strain is much smaller than the plane stress. This is for mode 1 Tressa criterion. Whereas if you use von Mises criterion, that is straightforward. For plane strain, this is the size of the plastic zone. Plane stress, it is comparatively higher. Okay. Again, you have to note that these are all normalized values. Ry by theta by k1 square by 2 pi sigma y square. Similarly, we can also plot for mode 2 as well. See here in mode 2, we have plane strain. Again, we need to establish the principal stresses. From the principal stresses, you need to make use of von Mises criterion in this case. So you see the plane strain plastic zone shape is relatively smaller than the plastic zone shape of the size of the plane stress. In the case of mode 3, it is one circle. That is by virtue of how we get the stress field solution ahead of the crack tip due to mode 3 crack. And you can see that it is a circle. Von Mises criterion will give you a circle. So that will be the shape of the plastic zone. So now Arvin saw the things from one perspective. Essentially, the idea was that if you could actually do a plastic zone correction factor for the crack embedded in elastic perfectly plastic material, we can be in a position to use LEFM principles. Okay, and then he, in the first instance, equated the stress to the yield stress, and he found out the value of lambda, but the equilibrium condition was not getting satisfied. Therefore, we had to do the second order estimate, and he obtained the value of RP. Once he obtained the value of RP, he found out that RP is nothing but 2 lambda. Okay, and then he had to extend the physical crack tip by a fictitious amount, that is lambda, in such a way that the equilibrium condition is still satisfied. The equivalence is established in both the fronts. In the front that we can still apply LEFM principles, therefore we can find SIF for the extended crack, and also we can equilibrate. There is a equilibrium between the extended crack and also the elastic singular crack tip stress field. There is an equivalence. So that sense, it is not violating the equilibrium. At the same time, it is able to actually extend the crack by lambda and accommodate the LEFM principles in that framework. Whereas in the strip yield model, that what we are going to see now, Duckdale and Barnablet, they viewed things from a slightly different perspective. In fact, both of them independently introduced cohesive strip zones. These are called cohesive strip zones extending from the crack tip. You can see there is literature in the reference that I mentioned on the either end of the slide. So what they assumed was that there is initial crack of length 2L. You see here, there is a crack of length 2L, but all the plasticity, is confined to this zone. They call this as strips. Okay. Therefore, the actual crack length is 2A. Okay. So, or in other words, if the crack length is the physical crack length is of 2L, we need to add some terms to it to realize that the actual crack or the end-to-end crack is 2A, which is more than 2L. So how do we get this? So what they did was very interesting. He broke this elastic, perfectly plastic problem with a crack in it into two elastic problems. Okay. Again, I repeat, initially there is a crack of length 2L, but on either ends you have a strip, and this strip is of finite dimension, and our objective is to find the dimension of the strip. How do we find it? Okay, once we find the dimension of the strip, we add to the original crack length of the physical crack length 2L, and we call that as the actual crack length. Okay, so now how do we find this strip length? What they did was they assumed certain things. Okay, as I said to you before, it is another perspective of looking into things to bring in this plastic zone correction factor so that we can still use LEFM principles. Now, these are the assumptions that they had. Plastic deformation concentrates in a line. So there are two lines. There are two strips at the either end of the crack tips. It is essentially a central crack inside of infinite geometry. So the plastic deformation is only confined to that strips, and it is suitable for thin plates. That means they have only derived this model for plane stress scenarios, and the material is again elastic, perfectly plastic. Okay, these are assumptions, and it has been found that the materials respond very well to Tresca yield criteria. Now, you see here, strip yield plastic zone is modeled by assuming a crack of length 2A plus 2 rho. So they have assumed initially itself, there is a crack of length 2A plus 2 rho. 2A is the physical crack, and 2 rho, this denotes the length of the strips, the summation of the length of the strips on either ends. So rho is the length of the plastic zone with a closure stress. There's a new term that has been brought now into picture, closure stress. What is this closure stress? I'll come into it later. And this closure stress are nothing but the yield stress applied at the end of each crack tip. Now, going into the Duckdale approach, what we see here is this. So, initially, they had a full crack, that is 2A plus 2 rho. Okay, so there was this linear elastic material, and they had a crack of length 2A plus 2 rho. Okay, so this is the first part of the problem. In the next part of the problem, what they did was they applied closure stress. Okay, again, it's an elastic problem, but here it is subjected to external load, far field loading of sigma. But in the second scenario, they have applied a closure stress or sigma y as yield stress. They have applied at the either end of the crack tip. Now you see, when you do this plus this, if you superimpose, what you are going to get is this. So it's a very interesting way of looking into a problem. Rather than actually solving elastic, perfectly plastic problem and the analysis of crack embedded in it, we can actually decompose that problem into finding the behavior of crack embedded in perfectly elastic material, but with certain loads, as I already shown to you there. So this is also shown in the figure, this figure as well. You can see here, initially there was a crack of length 2a plus 2 rho. It is subjected to far field loading of sigma, but in the next scenario, they applied a closure stress. Closure stress is the yield stress. So what it does is it tries to keep the crack closed. The crack surfaces, they are not opened yet. Okay, that is the effect of sigma ys. As I said to you before, the objective of all these models, Arvin's methodology or be it Duckdale-Barnard model / repealed model, our objective is to reduce. We have to eliminate the singularity. It is not reduce, I beg your pardon, it is eliminating the singularity. Okay, by eliminating the singularity, we make sure that there is no infinite stress ahead of the crack tip. That has been the principle in the Duckdale approach. You see here the net SIF due to the first case, first case is this one, and the second case, K rho, is this one, has to be equal to 0. In the first case, it is very easy. If you have a center crack of length 2a plus 2 rho in a infinite domain with tensile loading, far field tensile loading as sigma, then it is easy to find out what is the SIF. It is going to be given by K sigma, which is nothing but sigma into square root pi a plus rho. Okay, so that is straightforward. But in the case of second scenario, when there is actually only on certain regions of the crack face you have loading, what do we do? So in that case, we have some methods called as green function approach or stress function approach. So I'm not going into details of how we obtain this stress function. What I want to say is this. For certain scenarios, we have this stress functions. You see here, there is actually a crack, and it has some concentrated load intensities P. And in such scenarios, you can be in a position to find the SIF using some stress function approach. Okay, let us take it for granted that this stress function is known to us, or in certain other scenarios as well. Let us say if you have a crack like this, I'm not drawing the infinite domain, but I'm just drawing the center crack. If you have a concentrated load intensity, something like this, you will be in a position to find the SIF at this crack tip and also at this crack tip using this weight function approach. Okay, so now let us say for this problem, the SIF has been given like this. Okay, so we know the solution of theory. So now, having known the solution, is it possible to find the SIF in the second case? Second case meaning this one for this scenario, when the crack surfaces are partially loaded with sigma ys at either ends, at the extremities. Okay, so if you see this carefully, yes, it is possible to do. Why not? See, here you have load intensity. Now we are going to actually distribute, the load intensity. Add some more loads, and for each of these loads, you are going to have K1, and we are going to add them. That is how it is. But here it is, tensile, concentrated load intensity. But what we have here is, the compressive. It's a closure stress. That is why it is called closure stress. It's trying to close the, crack. So you see here in place of P, what did I put? Sigma ys into ds. Ds is the infinitesimal crack length, and then sigma ys is the closure stress acting on that strip. Okay, so nothing special. Have replaced P with sigma ys ds and K with dk rho. Okay, and if you observe carefully, this closure stress is only from from A to this is just a moment. Yeah. Okay. Okay, so it is A. From here it is A, and it is this length is rho. Okay, so you can see it is only loaded from A to A plus rho. Okay, so if you integrate this, if you actually integrate dk rho from A to A plus rho, you are going to get an expression like this. So this is going to be the SIF associated with the closure stress And we also had SIF associated with the far field loading for a crack of length 2A plus 2 rho, central crack. Okay, but according to Duckdale approach, even if you look at Arvin's methodology, our idea is to actually nullify the singularity. So that is why we have put an expression like this: K sigma plus K rho is equal to 0. So when you actually substitute these expressions, K sigma, and what is also K rho, we substitute these expressions, we are going to get a expression like this. Now, if you look at this expression carefully, there is this, we are interested to find this rho, right? So that is what we are interested. So how can you find rho from this? It is slightly a complicated expression. Therefore, we are going to make a small approximation that the far field loading is going to be much lesser than the yield stress, and your length of the strip is going to be much lesser than the length of the crack, half length of the crack. So if you make use of this assumption, you are going to get an expression like this. Finally, you realize the length of the strip in the case of Duckdale model is equal to pi by 8 K1 by sigma ys whole square. It is almost equal to RP. So this is nothing but RP in the case of plane stress, second order estimate. So that is how it is. So pi by 8 is approximately equal to 1 by pi. So that is why we are able. So finally, what we are able to show in the case of plane stress, both Duckdale model and the Arvin's methodology. So they both are able to actually give you a similar results. Then what is the difference between Duckdale model and Arvin's methodology? One difference is if your ratio sigma by sigma ys ratio, if it increases, then there is going to be some sort of difference, because this sort of approximation cannot be used. So then the results are going to be deviating. And I'll also show you one more difference in the effective crack length. Okay. So a summary, the first order model, first order estimate, we have this as the value of lambda, and for plane strain, this is what we had. And for Arvin's model, the second order estimate, we had RP as 1 by twice lambda. Because of the crack tip blunting, we got this value 1 by 3 pi K1 by sigma ys whole square. Once you consider the effect of crack tip blunting, you will get this expression. And for strip yield model, you got the value of RP, the length of the plastic zone, is going to be pi by 8 K1 by sigma ys whole square. So as I said to you, there is a perspective difference. The way Duckdale and Barnablet approached the problem to include the plasticity in that strip was slightly different from the way Arvin included. Now, I said already to you that in a scenario where your far field loading is almost sort of equivalent to yield stress of the material, then the Duckdale model and Arvin's model, they are going to differ. So that is one difference. The second difference is the effective crack length. You see, in the case of Arvin's model, the effective crack length has been A plus RP by 2 or A plus lambda. Whereas in the case of strip yield model, the effective crack length is A plus RP. There's a difference. Or is approximately equal to A plus 2 lambda. Now you can ask why this apparent difference. As I said to you, these are all models. In order to make use of the LEFM principles with ease, in spite of plasticity, such models have been introduced. How do we determine this crack tip plastic zone shape? Experimentally, you can make use of this etching technique or microscopy to estimate the shape of the plastic zone. You can see this literature, Hahn and Rosenfield, 1965. Or you can also see this literature. They were able to estimate the size of the plastic zone, shape of the plastic zone. And so that was, to a greater extent, it was in good agreement with whatever I have shown, the shape of the plastic zone. So that was the confidence in, Arvin's model or Duckdale model. The last part of the lecture is on the effect of plastic zone shape along thickness of the specimen. How does it affect the shape of the crack propagation? How does it affect the crack propagation? So if you take a thick specimen, if you have, let us say, thick specimen and you have a straight through to through crack, and if you apply a tensile loading, how does the crack propagate? So let us say if you have, so I'll go here. Yeah, so you can see here you have through thickness crack. So and then the crack is now the front of the crack front is a straight line. Let us say under the action of tensile loading, it is allowed to, let us say, propagate. What would be the shape of the crack front? With time, how does it evolve? See, on the extremities, on this surface, so let us say this is z-axis. This is z-axis, pointing inwards. So the surfaces which have z-axis as a normal, they are going to behave like a free surface because there is no external traction on the free surfaces. The surface that is visible to you, one in front of you, one behind the specimen. So that surfaces is kind of a surface which behaves like a plane stress. It is subjected to plane stress condition. Why am I saying that? Because the sigma zz, the applied traction in that direction is going to be 0. Therefore, in one direction close to the surface, you have one stress as 0, one principal stress as 0. Therefore, your material is behaving like a plane stress. If the material is behaving like a plane stress, the size of the plastic zone will be considerably higher. But when you go inside, internal, you see here, when you actually go inside along the thickness, if you travel and go inside of the material, because of the tensile load tries to contract. But it is not allowed to contract because of the resistance offered by its neighboring materials. Okay. Therefore, there is a generation of a third principal stress, the principal stress in the third direction. And that will introduce triaxiality. Triaxiality means what? Non-zero, principal stress on all directions. So that triaxiality is going to actually result in smaller sizes of the plastic zone. If the size of the plastic zone is smaller, then the rate at which the crack will propagate is going to be relatively higher compared to the scenario where the size of the plastic zone is bigger. So that is why if you allow the crack to propagate for some time, initially, you have this crack, through thickness crack, and if you allow to propagate, so it will propagate initially like this. Because as I said to you before itself, here because of the plane strain case, small plastic zone, it is propagating faster, and then it propagate like this. So gradually it will become like a tongue shaped. So that is how it propagates. That is the effect of triaxiality. The triaxiality sort of powers the rate of crack propagation. So just to summarize, what we have done is this: we have looked into Arvin's model, how we accommodated the plasticity, and also introduced the concept of effective crack to determine the SIF, effective SIF. But his perspective of looking into things was slightly different from how Duckdale and Barnett looked. So they assumed a strip yield model where at the either end of the crack, it was subjected to closure stresses. Specifically, it was sigma y as yield stress because it is elastic, perfectly plastic material. And they tried to calculate the SIF, the net SIF, and made it to 0 because in real materials you will not have infinite stresses. They cannot withstand infinite stresses. So that was the basis for the Duckdale model. So with this, I will stop. The Arvin's model and Duckdale's model have been completed. If you have any questions, you can ask me. Yeah, it is exactly 6:30 now.
Yeah, perfectly timed, Dr. Nelson.
Yeah, thank you, Sajjan.
Yeah, participants, if you have any specific questions, you can ask Dr. Nelson your questions. Dr. Rukhande, you raised hand in between. Perhaps you have some question for Dr. Nelson. No, Dr. Rokhande, are you around? Okay, he may not have any question. Any other participants who have any question for Dr. Nelson now? Yeah, it seems none of them have any question.
Okay, but you can always write to me if they have any questions. Share again.
What you wanted to see? Who was that? Just a moment.
There was one comment.
One Subhash Khetre. Yeah. Oh, he is asking about some other link. No. It is not about a question or something. Yeah. Okay. On behalf of all the participants, I'll ask you one question, Dr. Nelson.
Yeah.
Okay. Yeah. If you see the Irwin's correction, then he writes that A effective is equal to A plus lambda.
Yeah.
Can you please repeat the rationale for choosing the lambda equal to RP?
Okay. So yeah, I'll just share the screen again.
Yeah.
Yeah. So that's a good question, Dr. Sachin. So now you see here. Yeah. So essentially, as I said to you before, one of the principal objective for Arvin is to replace the crack of length A with a new crack length, so that LEFM principles can be still applicable. So what he did was, he extended the crack A by an amount lambda in such a way that, in fact, this, let us say, this length is L. We do not know what is this length. And only when you extend by lambda, it was seen that this area A1 and A2 will be equal. Now, what is this area A1 and A2? Had the crack been of length A plus lambda, and had it been in perfectly elastic material, that means if you use LEFM principles without diluting it, you would have obtained a stress field like this, Ky by sigma root 2 pi r along the crack line. And that would have corresponded to this one. Now, because of elastic perfectly plastic material, what has happened is that ahead of the crack, you have this sigma ys. Okay, this is the yield stress. That means the contribution due to the elastic stress field, the elastic stress field has been contributing this much, which is not being taken into account in elastic perfectly plastic material. So all that part above this line, sigma ys line, this has been sort of neglected, in elastic perfectly plastic material. So where does it go? You have to take into account of that, right? Because you are trying to make both equivalent. A plus lambda in LEFM is equivalent to A in elastic perfectly plastic material. So how are you going to actually establish the condition that this A1 has been taken into account somewhere? And the rationale is this: when you extend the crack of length A by lambda, this A1 has been taken into account in this portion.
Yeah.
So that has been the reason. It is almost equal. A1 is equivalent to A2. So the effect of the stress in this region to the force contribution has been already taken into account in this region, in this square region, when the crack has been extended from A to A plus lambda.
Okay.
So that has been the rationale. Or in other words, what you can say is, if you have a crack of length A plus lambda in elastic material, and if you have a singular stress field like this, this is equivalent. It is equivalent to a scenario when you have a crack of length A in elastic perfectly plastic material. So it will be like this. Both are equal. So that is what his premise was.
Yeah. Thank you.
Yeah. Thank you for the question. Thank you also participants for the time.
Dr. Nelson, there is a question from one participant. He
Yeah.
says that does isotropic behavior influence the crack propagation?
Isotropic behavior influence the crack propagation. That means see, essentially the crack is propagates when your SIF K, is greater than or equal to, critical SIF KIC.
Yeah.
So that is how it is. If you look from this perspective, the material properties doesn't come into picture here in K1, whereas KIC is a material property. Now KIC, whether it depends on the isotropic material or not, that we cannot say, but definitely K1 is not a property of the Young's modulus, material constants.
Yeah, it is independent.
It is independent. So in that sense, your crack propagation for for a crack in a linear elastic material, it should not be affected by the material constants. However, KIC is a material property.
Yeah, one more question has been actually written in the chat box now. He wants to ask what effect occurs due to hardness.
What?
What effect perhaps on K1C or K occurs due to hardness? That's what he is expecting perhaps.
Oh, okay. Yes. Yeah, there is a good correlation between hardness of the material and the fracture toughness. Yes, that is a good question. In fact, there are certain literatures that shows that they are correlated well. So if you are able to find out hardness for a material, you will be also in a position to find or estimate the fracture toughness KIC. But the exact relation, I'm not sure, but it is there.
Okay. Any other questions, participants? It seems, Dr. Nelson, there are no more questions. I take this opportunity to thank you for giving such a lucid and vivid explanation to every step, and the rationale for every action that is taken in the process of arriving at equations. It was indeed nice listening to you.